Right now, as you listen to this, a signal is traveling toward you. It left a spacecraft, a machine no larger than a small car, and it has been traveling for more than 23 hours. By the time it reaches the dish antennas on Earth that are waiting for it, that signal will have crossed more than 23 billion kilometers of empty space. It will arrive carrying a stream of data so faint that its power, by the time it touches the receiver, measures less than a billionth of a watt. Let that number live in your mind for a moment. A billionth of a watt. The light from a single candle flame at arm's length is approximately 10 million trillion times stronger than the signal Voyager 1 sends to Earth. And yet, every single day, engineers at NASA's Deep Space Network manage to catch that signal. They amplify it. They decode it. They reconstruct from its whisper a coherent stream of data about the boundary between our solar system and the interstellar medium, that vast, dark ocean separating our sun from every other star. That signal has been arriving with only a handful of interruptions for more than 47 years, and it will not arrive forever. This is the story of that countdown. The spacecraft we are talking about is Voyager 1, launched on September 5th, 1977 from Cape Canaveral, Florida. It weighed approximately 815 kilograms at launch, about the mass of a small car, and it carried a set of instruments designed to study the outer solar system, Jupiter, Saturn, and the moons of Saturn. It was supposed to function for 5 years. It has now been functioning for nearly half a century. In that time, Voyager 1 has traveled farther from Earth than any human-made object in history. As of early 2026, it sits at roughly 172 astronomical units from the Sun. That is 172 times the distance from Earth to the Sun. In raw numbers, that is approximately 25.8 billion kilometers. If you could drive there in a car at highway speed, the journey would take more than 29 million years. And it is still moving. Every year, Voyager 1 travels another 523 million kilometers deeper into interstellar space, moving at roughly 61,000 kilometers per hour. Fast enough that in a single second it covers more distance than the length of Manhattan Island. But here is what makes Voyager 1 unique among all the things humanity has ever built and sent into the cosmos. It is still talking. Every day its transmitter, powered by decaying plutonium converting radioactive heat into electricity, broadcasts a signal on a frequency of 8.4 gigahertz into the void. And every day, one of the 3 massive dish antenna complexes that make up NASA's Deep Space Network listens for it. In Goldstone, California. In Madrid, Spain. In Canberra, Australia. One of those 3 is always awake, always watching, always ready to catch the whisper. The signal travels at the speed of light. Even so, it takes more than 23 hours to cross the gap between Voyager and Earth. 23 hours, one way. That means when an engineer at JPL sends a command to Voyager 1, perhaps to perform a thruster maneuver or to adjust the pointing of its antenna, they must wait nearly 2 full days to know if it worked. 46 hours round trip from command to confirmation. You send a message, you go home, you sleep, you come back, you sleep again. And then, the next morning, you find out if the spacecraft heard you. This is what communication looks like at the edge of the known world. And that gap is growing every year. Voyager 1 moves another 500 million kilometers farther away. Every year, the signal takes a fraction of an hour longer to arrive. The clock is ticking not just on the spacecraft's power supply, but on the geometry of the universe between us. At some point, and the countdown to that point has already begun, the signal will stop. This is the story of when that happens and what it means. Before we can understand why Voyager's signal will eventually go silent, we need to understand what keeps it alive. Voyager 1 has no solar panels. At its current distance from the Sun, 172 astronomical units, sunlight is so faint that solar panels would be essentially useless. The Sun, from Voyager's perspective, is just the brightest star in the sky, still visible, still there, but no longer a useful source of power. Instead, Voyager 1 runs on nuclear batteries. More precisely, it runs on 3 devices called radioisotope thermoelectric generators, RTGs. Each RTG is roughly the size and shape of a large garbage can. Mounted on a boom extending from the spacecraft's main body, they contain pellets of plutonium-238, a radioactive isotope specifically chosen because of how it decays. Plutonium-238 doesn't produce dangerous gamma radiation the way other radioactive materials do. Instead, it emits alpha particles, relatively large, slow-moving particles that can be stopped by just a few centimeters of material. As those particles interact with the surrounding structure of the RTG, they generate heat. That heat creates a temperature differential across a set of devices called thermocouples. 2 different metals sandwiched together in a way that generates electricity when one side is hotter than the other. At launch in 1977, Voyager's 3 RTGs together produced approximately 470 watts of electrical power. That is roughly the equivalent of 5 conventional light bulbs running simultaneously. Not a great deal of power by human standards, but enough to run a sophisticated spacecraft's instruments, computers, and transmitters in the darkness of deep space. But here is the key constraint that has shaped Voyager's entire extended mission, and that now defines the countdown to its final silence. The power output of those RTGs declines over time, and it declines at a predictable, relentless rate. Every single year, the combined power output of Voyager's RTGs drops by approximately 4 watts. 4 watts per year, year after year, without exception. The plutonium is decaying, the thermocouples are degrading, and there is nothing anyone can do about it. This is not a malfunction, it is physics. Plutonium-238 has a half-life of approximately 87.7 years, meaning that after 87.7 years, half of the plutonium in each RTG will have decayed into other elements. After another 87.7 years, half of what remains will have decayed. The process is inexorable, gradual, and perfectly predictable. Voyager 1 has been flying for nearly 49 years. In that time, its RTGs have lost a substantial fraction of their original output. The spacecraft now operates on somewhere in the range of 250 to 300 watts. Roughly half of what it had at launch. That is not a lot of electricity. A modern laptop computer, while charging, consumes roughly 65 watts. The spacecraft that is humanity's farthest emissary into interstellar space is running on the power equivalent of a few charging laptops. And it is losing 4 more watts every year. This is the fundamental clock that governs Voyager's countdown. Not the distance, not the software, not the hardware wearing out from cosmic radiation. The fuel. The plutonium is dying, and when the power output falls below the threshold needed to run any instrument or maintain the transmitter, the signal will stop. Now, let us spend a moment with the other half of this equation, the machines on Earth that catch Voyager's whisper. The Deep Space Network, the DSN, is one of the most extraordinary pieces of infrastructure humanity has ever built, and one of the least celebrated. It consists of 3 complexes of enormous radio dish antennas placed at roughly equal intervals around the globe, so that as Earth rotates, at least one complex is always in position to receive signals from spacecraft in the outer solar system. Each site hosts multiple antennas ranging in size from 34 meters in diameter up to 70 meters, roughly the height of a 20-story building. These are not passive structures. They must be steered with extraordinary precision, pointing with sub-arc-second accuracy at targets billions of kilometers away, tracking the motion of spacecraft moving at tens of thousands of kilometers per hour. The 70-meter dishes are engineering marvels. Their surface must be maintained to millimeter precision across an area larger than a basketball arena. When the temperature changes from day to night, the metal expands and contracts, and compensation systems constantly adjust the dish surface to maintain that precision. Hydraulic systems that would dwarf a large crane move the entire structure to track the sky. When Voyager 1's signal arrives at one of these dishes, it is captured by a receiver cooled to within a few degrees of absolute zero, colder than the temperature of interstellar space itself, to reduce the thermal noise that would otherwise drown out the signal. The faint whisper from Voyager is amplified, processed, and decoded. What is remarkable is that this system works at all. The signal arriving from Voyager 1 carries less energy than it would take to lift a single sheet of paper 1 millimeter off a table. The information in that signal, data about magnetic fields, cosmic ray particles, plasma waves at the boundary of interstellar space, is encoded in the precise timing and modulation of an electromagnetic wave that crossed 23 billion kilometers of empty space, and the DSN catches it every day for 47 years. But the Deep Space Network is not simply a passive receiver. It is also the only way to send commands to Voyager 1. And in 2025, something happened that reminded the world just how fragile this two-way conversation has become. Between May 2025 and early 2026, the Deep Space Station 43 in Canberra, Australia, the only antenna on Earth capable of sending commands to both Voyager 1 and Voyager 2, went offline for major upgrades. During that period, engineers could receive Voyager's signal, but they could not reliably send instructions back. The spacecraft was, in a very real sense, beyond the reach of human commands for most of that time. Think about what that means. The one antenna large enough and powerful enough to reach Voyager 1 with a command went dark, and Voyager had to continue its journey alone, running on pre-programmed instructions, navigating the dark without the voice of home. The DSN will be restored. The upgrades are designed to extend the network's operational life through the 2030s and beyond. But the episode serves as a reminder that the countdown to silence is not just about Voyager's systems, it is about the entire infrastructure of connection. The dishes, the receivers, the engineers, the institutions that make it possible for a civilization to maintain a conversation with a machine at the edge of the solar system. Both ends of the conversation are mortal. Let us now lay out the full architecture of that countdown, because the silence of Voyager 1 is not a single event. It is a sequence of losses, a slow dimming, not a sudden extinction. Each phase of the countdown strips away another layer of connection between the spacecraft and the humans who built it. There are, broadly, 4 phases. The first phase has already begun. This is the gradual, systematic shutdown of Voyager's science instruments, the devices that actually measure things about the universe and send that data home. Voyager 1 launched with 11 science instruments. Most of those were turned off long ago, some after the planetary flybys of the 1970s and 1980s, others as power budgets tightened over the following decades. The cameras were shut down in 1990 after taking the famous pale blue dot photograph of Earth from beyond Neptune's orbit. At that point, the software that controlled the cameras was erased from the spacecraft's computer to free up memory and processing power. The computers on the ground that could interpret that software no longer exist. The knowledge required to operate them has dispersed. Even if Voyager's cameras could somehow be turned back on, we would struggle to know what to do with the images. By the late 2000s and early 2020s, the list of active instruments had dwindled to a small handful. The plasma wave subsystem, the magnetometer, the cosmic ray subsystem, the low-energy charged particle instrument. These 4 instruments measuring the charged particle environment of interstellar space were the last survivors of a scientific payload that once gave humanity its first close-up views of Jupiter's Great Red Spot and Saturn's intricate ring structure. In February 2025, NASA turned off the cosmic ray subsystem on Voyager 1. The low-energy charged particle instrument is expected to follow. With each shutdown, the spacecraft loses another way of seeing the universe. Eventually, only the magnetometer and the plasma wave subsystem will remain. And those two have a lifespan measured in years, not decades. The end of science data from Voyager 1 does not mean the end of the signal, but it marks the beginning of the final act of the mission. From that point on, Voyager 1 is no longer a scientific instrument. It is a transmitter, a heartbeat, a proof of continued existence. The second phase is the end of all science data. This is the moment when the last science instrument goes dark, not turned off by engineers managing a power budget, but simply no longer receiving enough power to function. At that point, the signal Voyager sends will contain only engineering telemetry, the spacecraft's vital signs, temperature readings, voltage levels, transmitter status, the equivalent of a pulse. This is expected to happen somewhere in the late 2020s or early 2030s. The precise timing depends on factors that are difficult to predict with certainty. The exact rate of thermocouple degradation, the performance of Voyager's power management systems, and whether additional emergencies demand unexpected power draws. Engineering data is still science in the same way that a patient's vital signs are still information. The temperature readings from Voyager's internal systems tell engineers something about the thermal environment of interstellar space. The voltage readings tell them something about the behavior of RTGs after decades of operation in deep space. Even in its final years of transmission, Voyager 1 will be teaching us something. The lesson will just be smaller and quieter and harder to hear. There is a question that tends to arise whenever people think seriously about Voyager 1 and its countdown to silence, and it is a question that sounds simple but opens into something vast. The question is this: does it matter? Does it matter that Voyager 1 goes silent? Does it matter, in any practical sense, that a small machine at the edge of the solar system stops transmitting? The data it sends is valuable to a small community of scientists. The engineering achievement it represents is genuinely remarkable. But in the ledger of things that affect the daily lives of the billions of people on this planet, Voyager 1 does not appear. It does not feed anyone, it does not cure anything. It does not resolve any of the urgent crises that compete for human attention and human resources at any given moment. So does it matter? The question deserves a real answer, not a reflexive one. And the real answer begins with a different question. What are the things that matter in a civilization beyond the immediate necessities of survival? Every human culture that has ever existed has maintained, alongside its practical efforts to survive and organize, a set of practices and objects and stories that serve no immediate survival function. Paintings on cave walls, monuments to the dead, songs for the harvest, prayers toward the sky. These things do not feed anyone, they do not cure anything, but they are not separate from the civilization that creates them. They are, in some deep sense, what the civilization is for. They are what the surplus of survival gets used for. They are the answer to the question, given that we are alive, what shall we do with that life? Voyager 1 belongs to this category of things. It is not a practical object in the way that a dam or a hospital is practical. It is an expression, one of the most extraordinary expressions in human history, of the human impulse to know, to go, to reach beyond the immediate and the familiar and the safe, and to send something into the unknown and to listen for what comes back. That impulse is not a luxury. It is not separable from the civilization that produced it. It is, arguably, one of the things that makes a civilization worth having in the first place. The curiosity, the reach, the willingness to build a machine that will outlast you by billions of years and to put your music on it and send it into the dark. When Voyager 1's signal goes silent, that reaching does not end, but something about its expression ends. The specific, concrete, daily evidence that we reached, that we built something and sent it out and stayed in conversation with it for nearly 6 decades, that evidence goes quiet, and the world becomes slightly different in a way that is hard to measure but real. It matters because the things that define us at our best matter, even when, especially when, they do not show up in any practical ledger. Let us also spend some time with what Voyager's countdown tells us about time itself, because the numbers involved in this story are strange in a particular way. They are not the incomprehensible numbers of cosmology, not the billions of light years that separate galaxies, not the trillions of years until the last stars burn out. They are numbers that sit in an uncomfortable middle zone, large enough to be humbling, but small enough to be personal. 10 years until the signal stops. 47 years of continuous transmission already behind us. 40,000 years until the closest stellar encounter. 5 billion years until the sun dies. These numbers span something like 14 orders of magnitude, 10 followed by 14 zeros. From the human scale of years and decades, through the geological scale of millions of years, to the cosmological scale of billions. And Voyager 1 occupies all of these scales simultaneously. It is a machine that was built by specific people in specific years, that will fall silent within the lifetimes of people already alive, that will make a stellar flyby in a time so remote it defeats imagination, that will still exist when the sun is a white dwarf cooling in the dark. This range of scales is itself a kind of data point about the nature of reality. The universe contains processes that operate on timescales from microseconds to trillions of years, and human beings, with their lifespans of decades and their civilizational memories of thousands of years, are tiny flickers within that range. But those tiny flickers can apparently build things that operate on a far larger range of timescales than the flickers themselves do. a plutonium battery decaying on a half-life of 87 years, a gold-plated copper disc lasting billions, a signal traveling for decades, a spacecraft traveling forever. The human moment is short. The reach of the human moment is long. These two facts sit together in Voyager 1 in a way that is deeply strange and, if you let it be, deeply moving. There is also something to be said about the specific nature of the countdown we are inside. This is not a countdown to disaster. It is not a countdown to impact, like an asteroid approaching Earth, or a countdown to failure, like a reactor running out of coolant. It is a countdown to completion, to the end of something that was never supposed to last as long as it has, doing more than it was ever designed to do, in places no one expected it to reach. Voyager 1 has been, by any measure, an overwhelming success. The mission it was designed for, a 5-year grand tour of the outer solar system, was completed on schedule and produced results that transformed planetary science. The extended mission, 42 additional years of interstellar exploration that no one fully anticipated, produced results that transformed heliospheric science. The spacecraft has not failed. It has succeeded beyond all expectation, and it will continue succeeding in a different mode until the physics simply will not allow it to continue any further. This is a different kind of countdown than the countdowns to disaster that more commonly appear in stories about the cosmos. The countdown to Voyager's silence is the countdown to the end of a gift that was given unexpectedly and generously by physics and engineering and the stubbornness of the team at JPL that refused to stop listening. A gift that lasted 47 years and that will last perhaps 10 more. It is a generous gift, and its ending, when it comes, will be a farewell rather than a catastrophe. Now, let us think about legacy. What does Voyager 1 leave behind apart from the spacecraft itself? The most immediate legacy is the data. Decades of measurements from the outer solar system and the interstellar medium, archived at NASA's planetary data system and available to researchers around the world. Images of Jupiter's moons that revealed volcanic activity and subsurface oceans and complex geology. Images of Saturn's rings that showed structures and dynamics no one had predicted. Measurements of the interstellar medium that have anchored our models of the heliosphere for decades. This data will be studied for a long time. Long after the signal stops, researchers will be returning to Voyager's archives and finding things in them that the original analysis missed. This is how scientific data works. It accumulates meaning over time as new questions are asked of old data and new methods reveal patterns that earlier tools could not detect. The data Voyager gathered will be part of the scientific conversation for decades, perhaps centuries, but there is a legacy beyond the data. Voyager 1 demonstrated something about what is possible in human exploration that has shaped everything that came after. It demonstrated that spacecraft could survive and function in the outer solar system for decades. It demonstrated that nuclear power systems could provide reliable energy for missions of this duration. It demonstrated that the deep space network could maintain communication across billions of kilometers. It demonstrated that human curiosity, backed by adequate engineering, could push past the immediate neighborhood of Earth and reach into the unknown. All of these demonstrations influenced the missions that followed. The Cassini spacecraft, which spent 13 years studying Saturn and its moons in extraordinary detail, built on what Voyager found. The Galileo spacecraft, which spent 8 years orbiting Jupiter and dropping a probe into its atmosphere, built on what Voyager found. The New Horizons spacecraft, which conducted the first flyby of Pluto in 2015, flew a trajectory made possible by understanding of the outer solar system that Voyager helped establish. Voyager's legacy is embedded in every outer solar system mission that has been flown since, and in the missions not yet flown, the potential future missions to the ocean moons of Jupiter and Saturn, the hypothetical interstellar probes that engineers dream about. The lesson of Voyager will be foundational, that you can go that far and come back with answers, that the distance is not prohibitive if the engineering is sound and the commitment is genuine. There is also a cultural legacy, harder to measure, but just as real. The pale blue dot photograph taken on February 14, 1990, when Carl Sagan persuaded NASA to turn Voyager 1's camera back toward the inner solar system for one last look, became one of the most widely reproduced and most philosophically significant images in human history. It showed Earth as a tiny, pale blue speck, suspended in a ray of scattered sunlight, indistinguishable at first glance from the background of empty space, easily missed if you didn't know where to look. Sagan's reflection on that image, the one that begins with the words, "Look again," at that dot, has been read and quoted and shared in the decades since, becoming a touchstone for a certain kind of cosmic humility. The recognition that everything human beings have ever done, every civilization and war and act of love and creative achievement, took place on that pale blue dot. That the dot is all we have had, and that it is fragile, and that we should treat it accordingly. That photograph was made possible by Voyager 1, by the engineers who built it, the scientists who designed its camera, the mission managers who agreed to turn the spacecraft around for one last look, the navigation team that calculated the precise pointing required to capture Earth against the background of space. And it will outlast Voyager's signal by as long as the image can be stored and transmitted and reproduced, which is to say, potentially, a very long time. The image endures, the signal ends, but the image would not exist without the signal. None of the enduring legacies of Voyager 1, not the data, not the photographs, not the cultural impact of the pale blue dot, would exist without the signal, without the daily, relentless, 47-year conversation between a small machine at the edge of the solar system and the dish antennas of the deep space network. The signal is the thread that connects the spacecraft to everything it has given us. When the thread breaks, we will still have what came across it, but there will be no more. Let us now think about future interstellar missions, because one of the natural questions that arises from Voyager's countdown is, what comes next? When Voyager 1 falls silent, what will replace it? Who will be the next emissary humanity sends into interstellar space? The answer, as of 2026, is complicated and somewhat uncertain. There is no dedicated, funded mission to interstellar space currently in development at any major space agency. The next spacecraft to be confirmed as entering interstellar space will likely be Voyager 2, which crossed the heliopause in 2018 and is now traveling through the interstellar medium on a different trajectory than Voyager 1. Voyager 2's RTGs are on a similar power curve, and its projected end of communication window is similar to Voyager 1's, mid to late 2030s. New Horizons, the spacecraft that flew past Pluto in 2015, is also heading for the outer solar system, though it is currently only about 60 astronomical units from the Sun, roughly 1/3 of the way to Voyager 1's current position. Its RTGs will give out sooner in terms of years of operation from now, meaning it may not reach the heliopause before it falls silent. Its trajectory and power profile make it an uncertain candidate for interstellar science. There are proposals, serious scientific proposals, developed by credible researchers and published in peer-reviewed journals for dedicated interstellar probe missions. These proposals typically envision a spacecraft smaller and lighter than Voyager, perhaps using advanced propulsion systems to achieve speed significantly faster than Voyager's 61,000 kilometers per hour. One class of proposals involves solar sail technology, using the pressure of sunlight to accelerate a thin, large-area reflective sail. If a solar sail-equipped spacecraft could be brought very close to the Sun before deploying its sail, close enough to receive a powerful, concentrated push from intense sunlight, it might achieve velocities several times greater than Voyager's. Another set of proposals, more speculative but genuinely studied, involves laser propulsion, using a powerful ground or space-based laser to push a small, lightweight sailcraft to velocities approaching a meaningful fraction of the speed of light. The Breakthrough Starshot initiative, proposed by scientists and technologists, including the late Stephen Hawking, envisions sending gram-scale laser sail probes to Alpha Centauri within a generation. These probes would pass through the Alpha Centauri system in hours and have almost no time to take measurements, but they would demonstrate the principle. Neither solar sails nor laser propulsion is currently ready for an interstellar mission at the scale of Voyager. The engineering challenges are substantial, the costs are high, and the scientific and political will required to fund such a mission does not currently exist in any organized form. But the ideas are alive. The proposals are being written. The calculations are being done, and the precedent set by Voyager 1, the precedent of going farther than seemed possible, lasting longer than anyone expected, and returning science that changed our understanding, is the foundation on which all of these proposals rest. Some future generation will send another emissary. They will build on what Voyager found and on what Voyager 1's decade of interstellar measurement established, and they will go farther and learn more and push the boundary of human knowledge outward again. But that is their story. Our story right now is the story of the signal that is ending, the conversation that has been ongoing since 1977 and that will fall silent, in all likelihood, within the next 10 years. Let us come back one more time to the immediate present, to the year 2026 and the years immediately ahead. In 2026, as mentioned, Voyager 1 will cross the 1 light day threshold. This milestone deserves a little more attention than we gave it earlier, because it opens a window into something philosophically interesting about the nature of communication at these distances. When Voyager 1 is 1 light day from Earth, and you send a signal to it, the signal takes 1 day to arrive. The spacecraft receives your message, processes it, and sends a response. That response takes 1 day to reach you. The total round-trip time for a single exchange is 2 days. Now imagine a conversation under these constraints. You ask a question. You wait 2 days for the answer. You send a follow-up. You wait 2 more days. A conversation that might take 5 minutes in person or 5 seconds via text message takes weeks across this distance. This is not an analogy or a thought experiment. This is the actual operational reality of communicating with Voyager 1 right now. Every command sent to the spacecraft begins a 2-day waiting cycle. Every diagnostic question begins a 2-day waiting cycle. Every thruster maneuver, every software update, Every power management instruction, all of it requires this patience. In the long arc of human communication history, nothing quite like this has existed before. Traders in ancient times waited months for messages to cross oceans. Diplomats in the 18th century waited weeks for responses to cross continents. The telegraph, the telephone, the internet, each collapsed the waiting time closer and closer to zero. And then, at the extreme edge of the space age, we pushed it back out again, not to weeks or months, but to days, across distances that no previous communication had ever crossed. And those days are getting longer. The conversation with Voyager 1 is slowing down year by year as the distance grows and the light travel time increases. What will be 30 hours by 2030? What will be 40 hours by the mid-2040s if the signal was still present, which it will not be? The conversation is ending not just because the power is running out, but because the geometry of the universe is stretching it beyond the point where it can remain meaningful. There is a beauty in this that is difficult to articulate. The signal reaches us, always, from the past. By the time it arrives, the moment it represents has already moved on. Voyager 1 is not where it was when it sent the signal we just received. It has moved another 1.5 million kilometers since that signal was sent. The Voyager we are talking to is always a Voyager of yesterday. This is true, of course, of all communication across distance. The light from the nearest star takes 4 years to reach us, meaning we see that star as it was 4 years ago. The light from distant galaxies took millions or billions of years to reach us, and those galaxies may have changed dramatically, may even have ceased to exist in any recognizable form in the time that light was traveling. Voyager 1, at 23 light-hours away, sits between these extremes, closer than the nearest star by a factor of many thousands, farther than anything else humanity has built by a factor of many hundreds. A middle distance, humanly speaking, close enough to communicate across, far enough that the communication takes a day and a half round trip. And it is in this middle distance, this liminal zone between the near and the unimaginably far, that Voyager 1 has spent its extraordinary career. Not among the stars, not orbiting a planet, but in the space between. In the long dark beyond the solar system and before whatever comes after. This is, perhaps, the most honest way to describe what Voyager 1 is. Not a spacecraft, exactly. Not a probe, exactly. But a traveller in the in-between. A presence in the space that has no name and no address and no features. The space that is simply the gap between things. The gap between our sun and the next sun. The gap between what we know and what we don't. It has been in that gap for more than a decade. It will be in that gap for billions of years after the signal stops, and it sent dispatches. That is perhaps the most remarkable thing. For the time that it had power, it sent dispatches from the in-between. It told us what the in-between is like in terms of magnetic fields and particle fluxes and plasma wave activity. It told us that the in-between is not nothing, that it has structure and dynamics and a physics of its own. It told us that the boundary between our solar system and the in-between is more complex and more turbulent than we imagined, and then, in a few years, it will stop sending dispatches, and we will be left with what it told us, and with the knowledge that it is still out there, still moving, still carrying its gold record, but silent. The dispatches will stop. The traveller will continue. In the quiet after the signal stops, in the months and years immediately following the last telemetry packet from Voyager 1, there will be, inevitably, a period of reflection and reckoning, not just in the scientific community, but in the broader culture, in the public conversation about space and exploration and the human place in the cosmos. That reflection will contain, almost certainly, some grief. The kind of grief that attaches to the end of things that have been present for a very long time. The grief of a generation that grew up knowing Voyager was out there and is now learning to know it differently, as history rather than presence, as legend rather than fact. But if that grief is honest, it will also contain gratitude, because the signal did not have to last as long as it did. The RTGs were designed for a 5-year mission. The spacecraft was designed for a 5-year mission. Everything beyond that was a gift from physics, from engineering, from the people who refused to stop listening, from the stubborn fact of plutonium-238, decaying on its slow, reliable schedule, producing just barely enough power for one more year, and then one more, and then one more. 47 years of that gift, perhaps 10 more to come. That is an extraordinary thing, and the right response to an extraordinary thing is not merely grief at its ending, but gratitude for its having happened at all. We had Voyager 1's signal for nearly 6 decades. We learned things from it that we would not otherwise have known. We saw things through it, Jupiter's moons, Saturn's rings, the pale blue dot of Earth that no human eye had seen before. We heard things from it, measurements of the interstellar medium, data about the boundary of the solar system that no instrument had ever gathered. We stayed in conversation with a machine that was farther from home than any machine had ever been, and we kept that conversation going far longer than anyone expected. That is not a tragedy. That is a triumph. The tragedy, if there is one, would be to let the countdown to silence pass without noticing it, to let the last decade of Voyager 1's signal go unremarked, unseen, unappreciated, to allow the whisper from 23 billion kilometers away to fade without anyone pausing to say, "This was remarkable, and it is ending, and we should know what we are losing." This video is in part a refusal of that tragedy, a refusal to let the countdown pass in silence before the silence comes. A pause, taken now, while the signal is still arriving, to acknowledge what it is and what it means. The signal is arriving right now, not metaphorically, not as a historical fact. Right now, as these words reach you, Voyager 1 is transmitting. Its RTGs are converting radioactive decay into electricity. Its transmitter is broadcasting on 8.4 gigahertz into the void. Its signal is traveling at the speed of light across 23 billion kilometers of interstellar space toward the dish antennas of the Deep Space Network. Somewhere in the Mojave Desert or the mountains of Spain or the Australian outback, a massive dish is pointed at the sky. Its receiver, cooled to near absolute zero, is listening at the right frequency, and it is catching that signal, a whisper from the edge of the solar system, a billionth of a watt, arriving across an ocean of space right now. This is not a story about something that happened. It is a story about something that is happening right now, today, in the present tense, and it is a story about something that will stop happening in the not distant future for the last time. When the last signal from Voyager 1 arrives at the Deep Space Network, when that final whisper crosses the 23 billion kilometer gap and touches the receiver for the last time, it will not be labeled. It will not announce itself as the last one. It will arrive as all the others have arrived. at the speed of light, carrying its faint cargo of telemetry, decoded and processed and archived alongside the hundreds of thousands of signals that preceded it. And then the next scheduled contact window will come, and the dish will listen, and there will be nothing. That is how it will end. Not with a dramatic final transmission, not with a prepared farewell message, not with any of the ritual closings that human beings devise for endings they can plan for, just the absence where the signal used to be, the nothing that follows the something. In that nothing, Voyager 1 will continue its journey, as it always has, as it always will, into the dark between the stars. The signal ends, the journey continues. And somewhere in the space between those two facts, in the gap between the mortal whisper and the immortal machine, between the few watts of power that kept a conversation going for nearly 60 years and the billions of years that conversation will echo through, somewhere in that space, if you are very quiet and you listen carefully enough, you can hear what it means to be a civilization that looks up. We looked up, we reached, we built something that could reach farther than we could, and we listened, for as long as physics allowed, to what that reaching found. But the window is narrow and closing. The third phase, and this is the one most people envision when they think about Voyager's final silence, is the end of communication entirely. This is when the RTGs no longer produce enough power to run the transmitter itself, and the signal that has been traveling toward Earth for nearly 5 decades finally stops. Current projections from NASA suggest that Voyager's RTGs may continue to supply enough electrical power to return engineering data until approximately 2036. That is roughly 10 years from now, as of 2026. 10 years during which the spacecraft will move another 5 billion kilometers deeper into interstellar space. 10 years during which the signal will grow fainter, the round-trip communication time will grow longer, and the power margin will shrink towards zero. And then there is a fourth phase, one that is rarely discussed, but that deserves careful attention. This is the possibility that the signal ends, not because the power runs out, but because the spacecraft can no longer point its antenna at Earth. This is the thruster problem, and it may bring the countdown to a close sooner than the RTGs would suggest. To understand the thruster problem, we need to understand how Voyager 1 stays pointed. A spacecraft in deep space is not naturally stable. There are tiny forces acting on it at all times, the pressure of sunlight, the faint gravitational tugs of distant bodies, the minute reaction forces from its own internal mechanisms. Left to itself, the spacecraft would gradually drift off course, its antenna wandering away from Earth, its signal lost. To prevent this, Voyager 1 uses a set of small rocket thrusters, jets of hydrazine fuel that fire in precisely calibrated bursts to correct the spacecraft's orientation and keep its antenna pointed toward Earth. This system is called attitude control. For most of Voyager's mission, the attitude control thrusters functioned without incident. But over decades of use, the hydrazine lines that feed fuel to the thrusters have been slowly accumulating deposits. Residue from the hydrazine combustion process building up over time, gradually narrowing the fuel lines like cholesterol in an artery. By the early 2020s, several of Voyager's primary attitude control thrusters had become so clogged as to be effectively unusable. The mission team at JPL, facing the prospect of losing attitude control entirely, performed a remarkable engineering feat. In September 2024, working with a spacecraft that takes 23 hours to receive a command, they executed a thruster swap switching from the clogged primary thrusters to a backup set that had not been used since 2018. The maneuver required a carefully choreographed sequence of commands sent across the solar system, each one timed to execute in a precise order with no possibility of real-time correction if something went wrong. It worked. But the backup thrusters are also aging, also accumulating deposits, also operating in a system that has no additional redundancy. In the words of Suzanne Dodd, Voyager's project manager at JPL, everything on board is now single string. There are no more backups, no fallback systems, no second chances. Every component that remains functional is the last of its kind on the spacecraft. And NASA has taken this threat seriously enough to begin modifying the spacecraft's software, reprogramming Voyager's onboard computer from Earth across 23 billion kilometers of space to reduce the rate at which hydrazine deposits accumulate. If the thrusters fail before the RTGs run out of power, the antenna will drift, the signal will fade, and the countdown will end. Not with a planned shutdown, but with a slow, gradual loss of contact as the beam swings away from Earth and the whisper becomes inaudible. That is a different kind of ending than power failure, and the timeline for it is less predictable, less certain, which makes it, in some ways, more difficult to sit with. Now, let us go deeper into what all of this actually means. Let us follow the timeline year by year, examining not just the technical countdown, but the human one, the story of the people who have devoted their careers, in some cases their entire adult lives, to maintaining this conversation. We are currently in the year 2026. Let us walk forward from here. In 2026, Voyager 1 will reach a milestone that has no precedent in human history. For the first time, a human-made object will be so far from Earth that a radio signal traveling at the speed of light will take 24 full hours, one complete day, to reach it. Voyager 1 will be, at that moment, one light day from home. One light day is approximately 25.9 billion kilometers. It is a unit of measurement that was, until now, essentially theoretical in the context of human exploration. We knew what a light day was. We could calculate it, write about it, imagine it, but we had never actually had anything out there. In November 2026, we will. There is something profound about this milestone that goes beyond the numbers. A light day means that even if Voyager could somehow see Earth in real time, even if its cameras were still functioning and pointed in the right direction, it would be seeing Earth as it was yesterday. The Earth it sees is the Earth of the past. The conversation it has with us is always a conversation across time as well as space, and that gap will only grow. By 2027, Voyager 1 will mark its 50th anniversary in space, 50 years since launch. 50 years since a Saturn V-derived rocket lifted this small machine off the surface of the Earth and began its long journey toward the stars. The engineers who built Voyager 1, who designed its circuits, calibrated its instruments, programmed its computers, were largely young people in the 1970s. Many of them are now in their 70s and 80s. Some have died. The institutional knowledge of Voyager's systems is held by a small, aging team, and the challenge of maintaining communication with a 47-year-old spacecraft built before the personal computer era is not trivial. The programming languages used in Voyager's onboard computers are archaic. The hardware architecture bears no resemblance to anything built in the last 40 years. Diagnosing a problem on Voyager 1 requires engineers who understand systems that most modern computer science curricula do not even mention. When Voyager's flight data system began producing garbled data in November 2023, the team that diagnosed and fixed the problem spent months working through the issue, sending test commands, waiting 2 full days for each response, iterating on a solution across a 23 billion kilometer gap. They fixed it, but it took 4 months, and it required a level of patience and expertise that is genuinely rare. The 50th anniversary of Voyager's launch will be a moment of celebration and reflection, but for the mission team at JPL, it will also be a moment of quiet reckoning. Because 50 years marks the point at which almost everything that could conceivably go wrong has either already gone wrong and been fixed, or is hovering on the horizon of near-term probability. The spacecraft is operating, in the words of its project manager, on the edge. The question for 2027 and beyond is not whether more problems will occur. It is which ones will be solvable and which ones will be the last ones. Between 2027 and 2030, the final science instruments on Voyager 1 will almost certainly go dark. The magnetometer, which measures the strength and direction of the interstellar magnetic field, and the plasma wave subsystem, which detects electron density and wave activity in the interstellar medium, are the last 2 active scientific eyes Voyager has on the universe. When they go offline, something irreplaceable will be lost. Not just the data, though the data is irreplaceable in its own right. Voyager 1 is the only instrument we have ever placed in true interstellar space, beyond the heliosphere, beyond the influence of our Sun, inside the space between the stars. The measurements it takes of the local interstellar medium cannot be replicated from Earth or from any other spacecraft currently in operation or planned. The next interstellar probe, if one is ever funded, built and launched, would not reach Voyager's current position for decades or centuries. What will be lost is something harder to name. It is the ongoing act of knowing, of asking questions and receiving answers from the boundary of the solar system. The universe has been talking back to us through Voyager's instruments for nearly half a century, and when those instruments go quiet, we will be left in a silence that is different from the silence that existed before we launched. Before Voyager, we simply did not know. After Voyager's instruments fall silent, we will know what we are missing. That is a different kind of not knowing. In the early 2030s, Voyager 1 will be transmitting engineering data only: voltage, temperature, transmitter status, the beep of a machine that is alive but no longer seeing. The spacecraft will be approximately 200 astronomical units from the Sun, 4 times farther out than Neptune's orbit. The signal will take close to 30 hours to reach Earth. The engineers at JPL who receive that signal will, in a sense, be receiving something more like a message in a bottle than a scientific broadcast. The content of the message is not the point. The fact of the message is the point. The fact that the machine is still alive, still transmitting, still out there in the dark. That is what the engineering telemetry says more than any temperature reading or voltage level. And then, as we approach the mid-2030s, the final countdown begins in earnest. The RTG power budget, already razor-thin, will be approaching the threshold below which even the most minimal systems cannot function. Engineers at JPL will face increasingly agonizing choices about what to keep running and what to shut down. The transmitter itself consumes power, not a great deal, but enough to matter when the total available power is measured in dozens of watts rather than hundreds. At some point, and no one can say exactly when because the precise rate of thermocouple degradation is not perfectly predictable. The power available will fall below the minimum needed to maintain the transmitter. The transmitter will fail to fire, the signal will not be sent. And on Earth, the dish antenna that was pointed at the sky listening will hear nothing. Not static, not noise, just nothing. The particular nothing of an absence rather than a presence. The frequency that carried Voyager's signal for nearly 6 decades will become just another quiet patch of the radio spectrum. Current estimates suggest this will happen somewhere around 2036, though some projections extend to the late 2030s if power management is aggressive and no unexpected failures occur. The uncertainty is genuine. This is not a simple calculation, but a complex function of physics, aging hardware, and engineering decisions that have not yet been made. But the window is clear. We are not talking about centuries. We are not talking about generations. We are talking about years, perhaps 10, perhaps 12, perhaps, if things go badly, fewer. The countdown to Voyager's silence is not a far future abstraction. It is a present tense reality. It is happening now. Let us now spend some time with the golden record, because any telling of Voyager's countdown that does not address the golden record is an incomplete telling. When NASA designed the Voyager missions in the 1970s, the scientists and engineers recognized that these spacecraft, unlike any before or since, would eventually leave the solar system entirely. They would cross into interstellar space and travel among the stars for billions of years, long after the civilization that built them had ceased to exist in any recognizable form. Carl Sagan, the astronomer and science communicator, recognized this as an opportunity unlike any other in human history. He assembled a team, including his collaborators Frank Drake and Anne Druyan, whom he would later marry, and they created something remarkable. They called it the Golden Record. The Golden Record is a 12-inch gold-plated copper disc attached to the outside of both Voyager 1 and Voyager 2. It is not golden because gold is beautiful, though it is. It is golden because gold does not corrode. In the vacuum of space, a gold-plated copper disc will survive essentially indefinitely, far longer than any organic material, far longer than most metals, far longer than the civilization that created it. On that disc is encoded a message intended not for any particular recipient, but for whoever, whatever, might one day find it. The record contains 115 images encoded as analog waveforms depicting the diversity of life on Earth, the structure of our solar system, human anatomy and reproduction, and mathematical concepts likely to be universal. It contains greetings in 55 human languages, from Akkadian, an ancient Mesopotamian language, to Wu Chinese. It contains sounds of earth, thunder, surf, wind, rain, crickets, frogs, birds, whales, the sound of a baby crying, the sound of a mother's first words to her child, and it contains music. 90 minutes of music from across human history and culture, Bach's Brandenburg Concerto, Beethoven's Fifth Symphony, Louis Armstrong playing Melancholy Blues, a Navajo night chant, a Peruvian wedding song, Georgian polyphonic singing, Australian Aboriginal songs, music from Senegal, Bulgaria, India, Azerbaijan, Japan, Chuck Berry playing Johnny B. Good. The record also carries instructions for how to play it back, etched into its surface as diagrams using the properties of hydrogen as a universal clock that any sufficiently advanced civilization could understand. All of this is on Voyager 1 right now, traveling through interstellar space at 61,000 kilometers per hour. The record is not for us. We know what it says. We recorded it. The record is for the future. Some future so distant that everything we know will be gone, and only this disk, spinning silently through the dark, will remain. Think about that for a moment. The signal from Voyager 1 will go silent in roughly 10 years. The golden record on Voyager 1 will survive for billions. The difference in timescale between these two facts, the mortal signal and the immortal message, is one of the most astonishing contrasts in the entire story of human exploration. We built a machine that will outlast us by geological epochs. We encoded our music and our greetings and our images of Earth onto a disk that will endure longer than our sun. And we managed to stay in conversation with that machine for a mere 50-something years before the conversation fell silent. We are the mayflies of the cosmos. We live for a moment and we reach for eternity. The golden record endures, but let us return to the signal, because the signal is what connects us here, now, to that machine. And the signal is what is ending. Let us talk about what the interstellar medium actually is, because Voyager is not traveling through empty space. It is traveling through something thin, diffuse, and scientifically extraordinary. And understanding that environment helps us appreciate what Voyager's instruments have been telling us and what we stand to lose when those instruments go dark. The interstellar medium is the material that fills the space between stars. It is not nothing. It is a very thin gas, mostly hydrogen with some helium and trace amounts of heavier elements threaded through with magnetic fields, energetic particles, and faint radiation. Its average density is roughly 1 atom per cubic centimetre, so diffuse that by terrestrial standards it qualifies as a more perfect vacuum than anything we can create in a laboratory. And yet it is not nothing. It has structure, it has dynamics, it has a physics of its own. Voyager 1 crossed into the interstellar medium in August 2012. This was confirmed in 2013 when scientists analyzing data from Voyager's plasma wave subsystem detected the density of the surrounding medium and found it to be approximately 40 times higher than the density of the plasma inside the heliosphere, exactly as predicted for interstellar space. That moment, August 2012, was the first time a human-made object had crossed into interstellar space. It was, in every meaningful sense, humanity's first contact with the universe beyond our solar system. Not contact with another civilization, not detection of another world. Just the simple, astonishing fact of crossing a threshold that no human-made object had ever crossed, entering the space between the stars. Since then, Voyager 1 has been measuring that space. Every day, its instruments have been recording data about the magnetic field direction and strength, the flux of high-energy cosmic ray particles streaming through the galaxy, and the electron density and wave activity of the local interstellar medium. This data is not just scientifically valuable, it is scientifically unique. No model, no remote observation, no theoretical calculation can substitute for an in situ measurement at the location where Voyager actually is. What Voyager has found has already rewritten our understanding of the heliosphere, the bubble of solar wind that surrounds our solar system and protects it to some degree from the full flux of galactic cosmic rays. The boundary of that bubble, called the heliopause, is more complex and more dynamic than we anticipated. It is not a simple spherical shell. It is a turbulent, asymmetric structure, compressed on one side by the flow of interstellar material and extended on the other. The data from Voyager 1's final years, the magnetometer and plasma wave measurements being taken right now as you listen to this, will contribute to models of the heliosphere that will inform our understanding of how stars protect, or fail to protect, their surrounding planets, including perhaps information relevant to the habitability of planets around other stars. This is why the shutdown of Voyager's instruments is not just sentimental. It is a genuine scientific loss. The data stream ends, and the universe at Voyager's location becomes, from our perspective, dark again. We sent a machine to the edge of the solar system. It told us things we did not know, and then it went quiet. And we were left with everything it had told us, and the knowledge that we could not ask follow-up questions. Not for a long time, at least. Now, let us discuss something that often gets overlooked in conversations about Voyager's final countdown, the human dimension of the mission team. There is a group of people at NASA's Jet Propulsion Laboratory in Pasadena, California, a small group by the standards of major space missions, who have devoted significant portions of their lives to keeping Voyager alive and communicating. Some of them have been working on the mission for decades. Some of them are among the last people on Earth who deeply understand the spacecraft's archaic computer systems and the peculiarities of its aging hardware. The knowledge required to operate Voyager 1 is not written down in any single document. It exists partly in technical manuals, partly in institutional memory, and partly in the heads of a small number of engineers who have been working with this spacecraft long enough to develop an intuitive understanding of its behavior. When something unexpected happens, and unexpected things happen regularly with a 50-year-old spacecraft in interstellar space, the team at JPL must diagnose the problem using data that is 23 hours old, implement a solution using commands that take 23 hours to arrive, and then wait another 23 hours to confirm whether the solution worked. The entire debugging cycle for a single intervention takes approximately 46 hours. If the first solution does not work, another 46 hours for the next attempt. This is a peculiar kind of engineering. It requires patience of a sort that is not commonly cultivated in modern technical culture, where rapid iteration and immediate feedback are the norm. Working on Voyager means accepting that you will never see the results of your actions in real time. You send a command, and then you wait. You wait 2 days, and then you see what happened. And you develop over time a tolerance for that latency that becomes something deeper than professional habit. It becomes a relationship with time itself. In November 2023, Voyager 1 began sending garbled data back to Earth. The signal was there. The carrier frequency was present, the spacecraft was clearly transmitting, but the data it contained was unintelligible. It was as if a person was speaking in a clear, loud voice, but in a language that had become scrambled. The team at JPL spent months working through the problem. They sent test commands. They waited 46 hours for each response. They analyzed the patterns in the corrupted data, looking for clues about what had gone wrong. Eventually, they identified the likely cause: a memory bank in Voyager's flight data subsystem. One of its 3 onboard computers had failed. A single corrupted chip in a computer designed in the early 1970s, operating in the radiation environment of interstellar space, had scrambled the system that translates raw data into the formatted signal the DSN could decode. The solution required reprogramming the onboard software to route around the failed memory bank, reprogramming a 50-year-old computer across 23 billion kilometers of space using commands that take 23 hours to arrive. They did it. In April 2024, Voyager 1 began transmitting coherent data again. It was one of the most extraordinary achievements in the history of spacecraft operations, and it received relatively modest attention in the general media. But for the people who worked on it, it was the culmination of months of painstaking, patient work, and a reminder that Voyager's mission continues not just because of physics and engineering, but because of the human commitment to keeping the conversation alive. That commitment will not be eternal. It cannot be. The engineers who understand Voyager's systems most deeply are, by definition, the engineers who have been working on the mission the longest, and thus, on average, the oldest. The institutional knowledge will eventually fade. The team will eventually be reduced to a handful of people, and then to none. This is another kind of countdown, quieter, less measurable, but just as real. The countdown to the moment when no one on Earth knows exactly how to talk to Voyager 1 anymore. When the conversation ends, not because the spacecraft falls silent, but because we no longer know how to listen. That moment has not arrived, but it is not unimaginable. Now let us zoom out, far out. Let us leave the countdown of years and decades and enter the countdown of millennia and billions of years, because Voyager 1's story does not end with the silence of its signal. It continues long after, in a form that is stranger and lonelier, and somehow more beautiful than anything that has come before. When Voyager 1's transmitter finally goes dark, whether in 2036 or 2038 or whenever the power budget finally collapses, the spacecraft will not stop. It will not slow down. It will not fall toward a planet or a star or spiral into any gravitational well. It will continue exactly as it has been continuing at approximately 61,000 kilometers per hour in the direction of the constellation Ophiuchus. It will coast for a very, very long time. In approximately 40,000 years, Voyager 1 will make its closest approach to a star other than our Sun. The star is called Gliese 445, a small, dim red dwarf in the constellation Camelopardalis. Voyager 1 will not enter orbit around it. It will not even come particularly close by cosmic standards. The closest approach will be approximately 1.6 light-years, roughly 4 times the current distance from Earth to Alpha Centauri. Gliese 445 will not notice Voyager 1, but Voyager 1 will have, for the first and only time, been in the vicinity of a star other than the one it was born near. Long after that, as thousands of years become millions, Voyager 1 will drift deeper into the galaxy. The stars around it will slowly shift positions as the galaxy rotates. The constellations visible from Earth, Orion, the Big Dipper, Scorpius, will gradually deform as Voyager moves and as the stars themselves move. Eventually, after millions of years, the sky visible from Voyager's perspective will bear no resemblance to the sky we see from Earth, and Voyager 1 will be entirely alone. No signal, no conversation, no mission. Just the physics of its trajectory, carrying it forward through the dark at a constant speed, in a constant direction, because there is nothing out there to stop it. The golden record will still be attached to it. The sounds of Earth, the thunder, the surf, the whales, the music, encoded in the grooves of a gold-plated copper disc, still intact. Still decodable in principle for anyone who knew how to read it. For billions of years, the spacecraft will coast. The Sun, which was once the brightest object in the sky as seen from Voyager, will grow dimmer as the decades and centuries and millennia pass. Eventually it will become just another star. indistinguishable from the others in the random scatter of the galactic field. Eventually, even that faint light will be lost in the background, and Voyager 1 will continue, alone, silent, carrying its golden message through a universe that has long since forgotten, if it ever knew, that it was there. In approximately 5 billion years, our sun will exhaust its hydrogen fuel and begin to expand into a red giant, swallowing the inner planets and scorching the outer ones. The Earth will be gone. The deep space network, long since abandoned by whatever, if anything, came after us, will be gone. The civilization that built Voyager 1 will be gone, in every sense of the word gone that matters. Voyager 1 will still be out there. It will have travelled perhaps 300 to 400 light-years from where it started, a tiny fraction of the diameter of the galaxy, which spans 100,000 light-years. It will not have reached any other star system. It will be floating in the interstellar medium, alone, carrying the last physical remnant of an entire civilization's moment of reaching outward. And in 5 billion years, if nothing disturbs its trajectory, if no star passes close enough to deflect it, if no dense molecular cloud alters its path, it will still be moving, still coasting, still carrying the record. This is what it means to build something with nuclear power and good engineering and a vision that looked past the immediate mission requirements. You build something that outlasts everything that created it. You build something that is, in the most literal sense, immortal. Not metaphorically immortal, not symbolically immortal, but actually immortal in the way that physics can be immortal, which is to say, it will continue until something acts on it, and in the emptiness of interstellar space. Nothing will act on it for longer than civilizations endure. The signal will be gone in roughly 10 years. The machine will last longer than the sun. This contrast is the heart of the story. Let us come back to the present, to the years between now and 2036, to the time we still have. Because there is something important to understand about this final window, this last decade or so of active communication with Voyager 1, that tends to get lost in the technical details of RTG power budgets and thruster clogging and DSN dish upgrades. This window is not just the end of Voyager 1's mission. It is, in a very real sense, the end of a chapter of human exploration that will not come again. The Voyager missions were products of a very specific moment in history. In the late 1960s, astronomer Gary Flandreau, working at JPL, identified a rare alignment of the outer planets that would occur in the late 1970s, a configuration that happens only once every 175 years, in which Jupiter, Saturn, Uranus, and Neptune are arranged in a way that would allow a spacecraft to visit all four in a single mission, using the gravitational slingshot of each planet to accelerate toward the next. This alignment would not occur again until 2153. NASA, recognizing the window, began developing the Voyager program, 2 spacecraft launched 16 days apart in the summer of 1977, designed to take advantage of this once-in-175 years alignment and conduct the first grand tour of the outer solar system. The alignment meant that Voyager 1 and Voyager 2 achieved speeds they could not have achieved any other way. By using Jupiter's massive gravity to slingshot outward and Saturn's gravity to slingshot further still, the spacecraft achieved velocities that would carry them out of the solar system within decades. The trajectory that puts Voyager 1 at 172 astronomical units in 2026 is a direct consequence of a planetary alignment that will not occur again for more than a century. No future mission can follow exactly the same trajectory. The door that opened in 1977 has closed. Future interstellar probes, if they are ever built, will have to find their own paths, using their own propulsion, without the gift of that alignment. The Voyager missions were, in this sense, a product of fortune as much as engineering. The universe offered a rare window, and humanity, improbably, had the technical capability to fly through it at exactly the right moment. That will not happen again. Not with Jupiter and Saturn and Uranus and Neptune aligned that way. Not in any of our lifetimes. And the spacecraft that went through that window, the spacecraft that took humanity's first close-up images of Jupiter's moons, that discovered active volcanoes on Io, and a subsurface ocean under Europa, and the complex nitrogen geysers of Triton, that spacecraft is now in its final decade of communication. We are watching the closing of an era. There is a way to measure the magnitude of that era that goes beyond the scientific discoveries. Consider this. Voyager 1's journey from Earth to its current position took 49 years. In those 49 years, the world changed beyond recognition. When Voyager launched, personal computers did not exist. The Internet did not exist. The smartphone did not exist. The Soviet Union still existed. The Berlin Wall still stood. The Human Genome Project had not been conceived. No one had ever sequenced a gene. Climate change was not a mainstream scientific concern. All of that happened, all of it, in the time it took Voyager 1 to travel from Earth to its current position in interstellar space. And during all of that time, the signal kept coming. Every day, while the world transformed, and civilizations rose and fell, and technologies made old technologies obsolete, and children were born who grew up and had children of their own. Every day, a whisper from the edge of the solar system arrived at a dish in the Mojave Desert or the Spanish Mountains or the Australian outback. Every day, a voice from 1977 said, "I am still here." And now we are approaching the end of that daily message. Let us talk about what happens in the immediate period, the next 3 to 5 years, because this is the window in which Voyager's story becomes most urgent. By 2027, as mentioned, Voyager will mark its 50th year in operation. At that point, the total number of science instruments still functioning will likely be 1 or 2 at most. The magnetometer, perhaps, still measuring the direction and strength of the interstellar magnetic field, the plasma wave subsystem perhaps still detecting electron density variations. These instruments require careful power management to keep alive, and each passing year makes that management more precarious. The team at JPL has been performing something analogous to triage, making difficult decisions about which systems to keep running and which to sacrifice to extend the mission a little longer. Every few watts saved somewhere translates in principle into a few more weeks or months of active operation. These are not abstractions. These are real decisions made by real people, with genuine consequences for what humanity knows about the space between the stars. The engineer who decides to shut down the last magnetometer on Voyager 1 will be making a decision that cannot be undone, a decision that closes a data stream that has been open for 5 decades. What is it like to be that person? What is it like to have the authority and responsibility to turn off the last scientific eye of humanity's farthest outpost? There is probably no exact analogue in human experience. The closest thing might be the decision to close an observatory. The last observatory of a particular kind, observing a particular patch of sky that no other instrument can reach. Or perhaps the moment when the last person who speaks a dying language takes their final breath and the language ceases to exist as a living thing. Something irreplaceable ends, and the person who makes that call has to live with the knowledge that they made it. The team at JPL does not speak much publicly about this dimension of the work. They are engineers trained in the language of technical problem solving, and the emotional weight of what they are doing tends to be expressed in compressed, understated ways. But it is there. In interviews, the mission's project scientists and managers speak carefully about the importance of the data. Voyager is still gathering, about the significance of the measurements, about the responsibility of stewardship. They do not say, "We are losing something we will never get back," but that is what they mean. In 2028 and 2029, the remaining science instruments will almost certainly have been shut down. Voyager 1 will be transmitting engineering data only. Temperature, voltage, transmitter status. The signal will still be coming, but it will be a different kind of signal now. Not a report from an explorer in unknown territory, but the beep of a machine maintaining its own pulse, the equivalent of a vital signs monitor in an intensive care unit, information about whether the patient is alive, with no additional content about the patient's experience, and yet even that pulse will be scientifically significant. The fact of the transmitter remaining active, the precise frequency it operates on, the exact timing of its transmission carries information about the spacecraft's behavior. The signal itself becomes a data point about the health of the RTGs and the stability of the attitude control system. The message becomes, "I'm still here." And for a machine that has been traveling for 5 decades at the edge of human knowledge, "I am still here" is not a trivial message. It is, perhaps, the most important message. By the early 2030s, Voyager 1 will be approximately 190 to 200 astronomical units from the Sun. A signal from Earth will take approximately 28 to 30 hours to reach it. The round-trip communication time will have stretched to nearly 60 hours, 2.5 days from command to confirmation. At this distance and with this level of latency, the concept of active mission management becomes increasingly strained. You cannot effectively navigate a spacecraft in real time when your feedback loop is 2.5 days long. The mission team will be less an active control room and more a monitoring station, watching the vital signs, sending occasional commands, hoping nothing goes wrong that requires a rapid response. The Deep Space Network, upgraded through the mid-2020s, will still be capable of receiving Voyager's signal. But the infrastructure required to maintain this capability is not free. It requires staffing. It requires maintenance. It requires budget allocation in an era of many competing priorities. The question of how long NASA and the broader scientific community will continue to dedicate Deep Space Network time to a spacecraft sending only engineering telemetry, especially if budgets are constrained and newer missions are competing for antenna time, is a question that will become more pressing as the 2030s progress. It is possible, though the official position is that the mission continues until the power gives out, that the institutional decision to maintain continuous monitoring will be revisited before the physics forces the issue. And then there is 2036, the year that currently sits at the center of the countdown, the year that NASA's own projections identify as the approximate boundary of Voyager's operational lifetime, the point beyond which the RTGs are unlikely to produce enough power to maintain any functioning system. Approaching 2036, the scenario at JPL will be something like this: A small team of engineers, smaller than the team that operates most active missions, will be monitoring Voyager's telemetry as it arrives, one day after it was sent, from a distance of approximately 210 to 220 astronomical units. The signal will be even fainter than it is today, not because the transmitter has weakened. The transmitter operates at a fixed power as long as it functions at all, but because the spacecraft is farther away, and the inverse square law means that signal strength decreases with the square of distance. The power budget on board will be critically low. The RTGs will be producing perhaps 150 to 180 watts of electrical power, a fraction of what they produced at launch. The transmitter, the attitude control system, and whatever minimal computing function remains will be consuming almost all of it. There will be essentially no margin. On a day, perhaps in 2036, perhaps in 2037, engineers will notice that something has changed in the telemetry. Perhaps the signal will become intermittent. Perhaps the power readings will show a sudden drop. Perhaps the spacecraft's attitude control system, finally unable to maintain alignment against the faint forces acting on it in interstellar space, will allow the antenna to drift, and the signal, always thin and fragile, will become thinner and more fragile until it fades below the noise floor of the deep space network receivers. Or perhaps, and this is the more optimistic scenario, the spacecraft will maintain contact right up until the moment the transmitter goes dark, and one day the signal will simply not arrive. The dish in Canberra or Goldstone or Madrid will be listening at the right frequency, at the right time, and there will be nothing, and the engineers will wait. They will try different frequencies. They will check their own equipment, verify that the DSN is functioning correctly, confirm that there are no atmospheric or local radio interference issues, and eventually, after enough of that due diligence has been exhausted, they will conclude what they already know is true. The signal is gone. This will not be a surprise. It will have been anticipated for years. There will have been discussions and planning, and perhaps a ceremony of some kind, a formal acknowledgement that the mission has ended. But knowing something is coming does not fully prepare you for it. The day the signal stops will still be a moment unlike any other in the history of the space age, because it will be the moment when humanity's longest conversation with a spacecraft ends. 47 years of daily contact, 47 years of whispers from the edge of the solar system and beyond, 47 years of a machine saying, with clockwork regularity, "I am still here." And then it will be quiet, not the quiet of a mission that was completed as planned. Voyager completed its original 5-year mission in 1982. Everything since has been a bonus, a gift from physics and engineering and the relentless dedication of the people who kept the mission alive. Not the quiet of failure. Voyager 1 will have been the most successful spacecraft ever flown, by almost any measure you care to use, but the quiet of an ending, the quiet that follows the last word of a very long story. There will be people alive in 2036 who are children now. Those children will grow up in a world where Voyager 1 is still transmitting, still a daily presence in the background of human awareness, still the farthest flung ambassador of the civilization that built it. And then, in the course of their adult lives, the signal will stop, and Voyager 1 will become historical rather than present, a fact from the past rather than a daily reality. They will be the last generation for whom Voyager's signal is a living thing. After them, every generation will know Voyager 1 only as history, as a story. As a spacecraft that went farther than any other and talked for longer than seemed possible, and then fell silent as all things must. But here is what does not end. The spacecraft itself continues. We have already noted this, but it bears dwelling on, because the contrast between the mortal signal and the immortal machine is one of the most philosophically striking aspects of this entire story. After the signal stops, Voyager 1 will continue on its trajectory at roughly 61,000 kilometers per hour. It will not slow down, it will not stop. It will not decay in orbit as satellites in low Earth orbit do when atmospheric drag gradually pulls them down. There is no atmosphere in interstellar space, there is nothing to slow it. The only forces acting on it will be the gravitational influence of distant stars, which will slightly bend its trajectory over millennia, but never stop it. In 40,000 years, Voyager 1 will have its closest encounter with Gliese 445, the red dwarf in Camelopardalis. That star is currently 17.6 light-years from Earth. Voyager 1 will not enter orbit around it. It will simply pass through the star's gravitational neighborhood within roughly 1.6 light-years and continue on. No sentient observer is known to be in that system. The passage will, in all likelihood, be unobserved. In 300,000 years, Voyager 1 will have traveled approximately 17 light-years from the Sun, roughly the distance to Gliese, 445 today. It will still be carrying the golden record. The record's encoding will still be intact. The diagrams explaining how to play it back will still be etched into its surface. The sounds of Earth will still be stored in its grooves. In 1 million years, Voyager 1 will have travelled approximately 54 light-years from the Sun. The Sun, viewed from Voyager's position, will have become a fairly ordinary-looking star among the field of stars in the direction of its origin. In 10 million years, Voyager 1 will be roughly 540 light-years from the Sun. Humanity, if it exists in any form at all, will be almost entirely unrecognizable. The civilizations of the 21st century will be as distant and legendary as the first humans of the African savanna are to us. The record will be intact. In 100 million years, Voyager 1 will be approximately 5,400 light-years from the Sun. The Earth's surface will have been completely transformed by geological processes. New continents will have formed. Species alive today will long since have been replaced by descendants that bear no resemblance to their ancestors. The human species, in its current biological form, will almost certainly be gone. The record will be intact. In 1 billion years, Voyager 1 will be approximately 54,000 light-years from the Sun, more than halfway across the galaxy. The Milky Way will have begun its merger with the Andromeda Galaxy, a slow gravitational dance that plays out over billions of years, during which stars and star systems pass through each other with only rare, actual collisions. The night sky, as seen from what was once Earth, will have been dramatically transformed. The record will be intact. In 5 billion years, when the Sun expands into a red giant and the Earth is consumed, Voyager 1 will have travelled approximately 270,000 light-years. It may, by then, have drifted into the halo of the merged Milky Way Andromeda Galaxy, far above or below the galactic plane. The stars around it will be sparse. The universe will be a different place. The record will be intact. This is what human beings did in the 20th century. With the mathematics they had developed over thousands of years, with the engineering knowledge accumulated over centuries, with the rockets and computers and radio transmitters and plutonium batteries built in a few extraordinary decades, they sent a message into the deep future. A message that will outlast every monument ever built, every library ever assembled, every civilization ever organized. A gold-plated copper disc with the sounds of a blue planet and the songs of a species that reached, briefly, for the stars. And a signal that lasted against all odds. For nearly 6 decades, the signal is ending. The message endures. Let us bring this back to the human scale one more time. Let us talk about what it feels like to be alive during this countdown, what it means to live in the last decade of Voyager 1's active transmission. Most of us do not think about Voyager 1 on any given day. It is not part of the daily texture of life. It does not appear in news feeds, does not affect the price of groceries, does not have anything to say about politics or culture or the countless small urgencies that fill ordinary human lives. But it is there. Every day, reliably, it sends its signal. Every day, the Deep Space Network catches it. Every day, engineers at JPL look at the telemetry data and confirm that the spacecraft is alive and on course. There is something remarkable about the constancy of this. In a world defined by volatility, by the rapid churn of events and technologies and cultural moments, Voyager 1 has been the same, doing the same thing for nearly 50 years. It has not changed its story. It has not evolved into something new. It has been a spacecraft traveling through space, sending data home, day after day after day. This constancy is, in its way, a kind of anchor, a reminder that there are processes in the universe, physical processes, but also human processes built on a physical foundation that are not subject to the fluctuations of history. Voyager 1 was sent into the solar system on a trajectory that was calculated once and has been essentially unchanged since. The physics that governs its motion does not negotiate with current events. For the duration of our lives, Voyager 1 has been out there. For the duration of many of our parents' lives, it has been out there. For children born today, it will be out there throughout the entirety of their childhood and adolescence, and perhaps into their early adulthood. And then, for those children, it will stop. They will be the last generation to grow up with Voyager 1 as a living presence. The last people who can say with literal accuracy that right now, today, Voyager 1 is out there sending a signal and someone is receiving it. What will we make of that silence when it comes? There will be tributes, certainly, articles and documentaries and educational content. The kind of retrospective attention that significant endings tend to generate. People who never thought much about Voyager 1 during its active years will find themselves moved by the finality of its silence in a way they might not have expected. This is a common pattern with things we take for granted. We do not notice them when they are present. We feel their absence when they are gone. The background hum of a thing we assumed was permanent becomes audible only when it stops. Voyager 1 has been that hum, the background presence of humanity's farthest reach, the constant, quiet evidence that we once looked at the stars and decided to go. When it stops, we will hear the silence. But perhaps the more important question is what we do before it stops. What we do with the remaining years of the signal's existence, how we think about this last chapter of an extraordinary journey. One answer is data. The science instruments that remain active, the magnetometer, the plasma wave subsystem running on diminishing power, measuring the interstellar medium from a position no other instrument has ever occupied, are still gathering information that cannot be gathered any other way. Every day, of continued operation is a day of irreplaceable data. The scientific community understands this, and the mission team understands this, and the decisions being made right now about power management and instrument prioritization reflect a genuine commitment to extracting as much scientific value as possible from the remaining time. Another answer is memory. The remaining years of Voyager's signal are an opportunity to tell its story, to bring the significance of this mission to a broader audience than the one that has been following it closely. Most people know, in a vague way, that Voyager 1 exists and that it is very far away. Fewer people know the full arc of the story. The 1977 launch, the grand tour of the outer solar system, the pale blue dot, the crossing into interstellar space, the ongoing data stream from the interstellar medium, the decades of problem-solving and engineering heroism. Telling that story in the years before the signal stops feels important, not as eulogy, but as witness, as acknowledgement that this thing happened, this extraordinary thing, and that we were here for part of it. And a third answer, perhaps the most quietly radical one, is attention. Simply paying attention, simply being aware, in whatever small way is accessible to each of us, that right now, today, a signal is traveling from the edge of the solar system toward Earth. That a machine built nearly half a century ago is still alive and still talking. That the conversation humanity began with that machine on September 5th, 1977, is still ongoing. For a little while longer, it is still ongoing. The signal that arrives on Earth from Voyager 1 today left the spacecraft more than 23 hours ago. By the time you hear these words, the signal that was sent while you were listening has not yet arrived. It is traveling right now across 23 billion kilometers of empty space at the speed of light, carrying its faint cargo of data about the interstellar medium. In 23 hours it will arrive, and the engineers at the Deep Space Network will catch it, amplify it, decode it, and confirm once again that the spacecraft is alive. Tomorrow, another signal, and the day after that, and for approximately 10 more years. This is the countdown, not a dramatic detonation, not a sudden end, a slow, gentle diminishment, like a candle burning down, not in darkness, but in the vast, patient light of the universe it was always trying to illuminate. Voyager 1 was built to last 5 years. It has lasted 50. It will last in signal approximately 10 more, and then it will last in silence and in physics for longer than the sun. We built a machine that will outlast its creators by geological epochs. We kept it talking for nearly 6 decades. We listened to everything it had to say, and when it finally goes quiet, it will not disappear. It will continue, alone, dark, and carrying its golden record into the deep future. The signal ends. The journey doesn't. And somewhere in the space between those two facts, the mortal signal and the immortal journey, there is something that says more about what it means to be human than almost anything else we have ever done. We reached. We built something that could reach farther, and we listened, for as long as we possibly could, to what that reaching found. The signal is ending, but it has not ended yet. It is still coming. Right now. 23 hours from the edge of the solar system at the speed of light, toward the dish antennas in the Mojave Desert and the Spanish mountains and the Australian outback. Still coming. For a little while longer. Still coming. End of script. Total characters, approximately 100,000 estimated read time at ambient narration pace. Approximately 2 hours.